And so we can begin. I see the quorum, we're about 30. I hope the other guys will join in because it's very important that now that we have missed quite a number of classes, we should be able to catch up. Now, I want to believe that you spent the week that I gave you last week to do some useful work and do your own revisions. However, it's time now that we continue with our discussions and try and catch up as much as is possible before we lose a lot of time. Now, if you remember, our discussion last time was on the programmable logic controllers, specifically on the construction of a ladder diagram. And the example that we were looking at is that of controlling a motor. The last illustration we gave was how one could use a latching logic to be able to control a motor. We explained what a latching logic is, and we even gave the different types of latching circuits that exist, but we made use of one very common type of latching circuit. So I'll not go back to that because that is already in your notes. What I want to do is share with you a different type of control that we could incorporate into our circuit. So that is the timer. So today I want us to discuss the timer. Once we are done with discussion on the timer, then we look at how we can incorporate it into our circuit. Because now we have a circuit or a motor that we can control using a latching logic. But what if we want to incorporate a siren that needs to go off at a particular time before the motor begins? So that is why we need a timer. And then we'll continue from there. So PLC timers are just instructions that we use to control and operate any device. And this is when you want to operate a device for a specific duration. So I would say that PLC timer is an instruction. And so used to control and operate a device for a specified period. Okay, so because you have the timer, you can perform any specific operation that you want for a particular time span. So this is one of the most essential instructions or entities that you'll find in a ladder diagram. In fact, I don't remember seeing any ladder diagram that does not have a timer in it. In most cases, the ladder diagram is going to be needed. I mean, the timer is going to be needed while you're constructing your ladder diagram to control anything. Now, we have to see what kind of timers we need, because the operations or the devices that we want to operate usually need different types of operations of the timer. So we need different types of timers to suit our different needs in regards to controlling these devices. So there are three types of a PLC timer. The first PLC timer is known as the on delay. Some books abbreviate it as TON, on delay timer. We also have, apart from the on delay timer, you could guess that we have the off delay timer. Again, abbreviated And then lastly, we have what we call the retentive timer. But in the full name is retentive on off timer, abbreviated as RTO. So, ladies and gentlemen, these three are the types of timers that we often make use of while we are programming instructions into a ladder diagram to control devices for a specified period of time. The three have their own unique properties, and so and even the diagram that we use to represent them are also unique. So we need to quickly look at that, and then we move on to how we can apply it into a ladder diagram so that we see how important each of these can be in any scenario. So let's start with the on delay timer. Perhaps one of the most common timers that exist, the on delay timer. Okay. Now, this timer is used especially when you want to start what we are calling momentary pulses. You want to start some pulses for only a short period of time. The basic diagram that we use for this timer is and sometimes, usually, please take note that the diagram or the block diagram that we use to represent this timer sometimes vary based on the manufacturer of the PLC, but the variation is not too much. So usually there's only one input. So you get a timer input. Now, different manufacturers will call it different names. Of most importance is because we are going to have other instructions in PLC other than timers, usually we use a block diagram to represent those instructions. I know we've come across the normally open contact, normally closed contact. We've come across the coil or the output or the different types of outputs. But now we are looking at instructions that we use block diagrams to represent. And when we use these block diagrams, we need to label them so that differentiates what the device is. So in this case, we have to indicate that this is the on delay timer, okay? Or some people call it timer on delay. Timer on delay. Now, there are specific features that exist in this timer, very specific features. These features include, let me just put them here. Within this timer, we need to have a timer. They have different abbreviations depending on the type of PLC or manufacturer, but there's a timer in there. There's a time base. For those of you who have operated an oscilloscope, you know what a time base is. Then you have a preset function, and you also have an accumulator function. Okay, but also on the output, you have two things. You have what we call the enable output. So this is the timer output itself. Timer output. We also have what we call a done bit. So EN stands for enable, and DN is a done bit. Okay, it's a done bit. So these are the main features that must exist in your PLCs. Okay. So every time you want to use a device, and in that device, you want to ensure that they're going to have some momentary pulses for a set period of time. You want the device to come on for a certain period of time. You need an on delay timer. One typical example that you make use of is in the traffic lights. So you want the red signal to be on for a period of time, then it goes off, maybe then followed by the green, then definitely you need an on delay timer. But remember the key features. These features might be some of the manufacturers might have different features, but the key ones are the timer. The timer must exist. Some books abbreviate it as TT. Okay, you must have a time base, you must have a preset button, and you must have the accumulator. Now, it could be, maybe it should be important that I mention to you why each of these is important. So every time you use a timer, the timer itself from the word will start counting. So the timer is responsible for counting the amount of time that is elapsing, or it will be helping us know how much time has elapsed. Okay, or it's the counter. It's actually the counter. It's counting. Okay, this is the counter. Okay, but it's a time counter. It's actually counting the time. Now the time base, this one gives you the intervals of count. The intervals of count. Because if I want a timer to count 10 seconds, I can decide that if I want it to count 10 seconds in steps of 1 second, so therefore there'll be 10 counts, because I want to achieve 10-second count, but at intervals of 1 second. So at the end of the day, I'll achieve 10 counts, meaning the timer here need to click 10 times. But the time base here sets the interval of count, such that the timer count multiplied by the time base should give you the amount of time you want. Okay, so you have 10 times 1 equals to 10. So this 10 was the TT. This is the time base. And this is the total time. Okay, this is the total time that you want. Now, to make it more interesting, we have two more features in the timer that are also equally very important. Two more features. That is the preset. So you have the preset, which you can imagine is used to, after a count, after the count has been reached, there's a preset value. So if I wanted to count 10 seconds or 15 seconds, that is entered here. So it's the preset value that you want to achieve. So every time maybe you want your timer to count 15, then the preset is set at 15 seconds. That's the preset value, the value that you intend to achieve its count. The time base will give the intervals of that count. And of course, the TT or the timer is the one that counts, is the one that actually moves. The accumulator, on the other hand, gives you the amount counted so far. Okay, so this is the time, the elapsed, I'll just say elapsed time. Okay, how much have you counted at one point? So every time you count, and remember, each of these have memory locations. There's a memory address associated with them. So the accumulator is used to store the amount that has already been counted. So if you are counting to 15 seconds as has been preset here, if we have reached 10, then the elapsed time here will be having 10 seconds, so that we know that only 5 is remaining. So let's say here we set it at 1 second, meaning it's counting at intervals of 1 second. The value we want to achieve is 15 seconds. And maybe as we speak, we already have 10 seconds counted. Okay, so we'll see how the accumulator helps us a lot. We'll see it especially with the done bit, because as soon as the accumulator value reaches the preset value, meaning if this reaches 15 seconds, then the done bit goes to a logic high, meaning we are done counting. So as soon as you reach the count that you wanted to achieve, then the done bit goes to a logic high, or what we're saying is a logic 1, or it's activated. And that happens when the accumulated value equals the preset value, to show the timer that we have achieved the count of time that we wanted. So the done bit goes to a logic 1. And so we'll see what that then means in translation to the output, okay, of the timer, all right? So that is basically the the timer on delay or on delay timer. It doesn't matter the sequence. Some books call it timer on delay. Some call it the on delay timer. It's fine. There's no problem. The other one is the off delay timer. Now, the off delay timer is like the opposite of an on delay timer. In the off delay timer, we use it as an instruction. I told you these timers are PLC instructions. So we use it as an instruction when we want to switch off the output after a certain amount of time. I gave you an example. If I want to watch the TV or I'm listening to my music, I can set it such that after a period of time, it's going to automatically switch off. So basically, if I were to implement that using a PLC instruction, then I will use the off delay timer, because it is used to switch off the output or to turn off the output of a system after a certain amount of time. So again, because it is a block diagram that we use to represent this instruction, it is important to label it whenever you use it. Again, it also just has the timer input. Then, of course, it has the enable bit, which is the timer output. That you should know it's standard timer output. Then we have the done bit. Okay, so this is the timer off. You can call it timer off delay. And it must also have the TT. Of course, because that counts, it must still have the time base. I've told you that gives you the interval of count, the preset value, the amount of time you want to count to before the system goes off, and the accumulated value, the amount you've counted so far, the amount of time that has elapsed. Okay, so you can see that the difference between the off delay timer and the on delay timer, aside from their function, is the labels are almost the same. That is why it is important that you actually indicate here. If you don't indicate this, then I might assume that's an on delay timer. Okay, and yet that is of a different instruction. Again, I'll emphasize that you might see a slight variation in the way they are labeled based on the manufacturer. Maybe this is Allen Bradley, but Siemens will have a different variation in their labeling, but the functions remain the same. They all must have an input, they all must have an output, they all must have a done bit, they must have an accumulator, they must have a preset, they must have a time base, and they must have the timer itself. Okay, so please take note of that as well. I've told you this is used to have a system being switched off after a certain period of time. If you are, for example, in a company and you're working in quality assurance, and you want that every 1 hour, the whole conveying system stops, the conveyor belt stops, so that you can come into the production line and sample the products to ensure that they are keeping up with the quality that is expected or the standards that are expected, then you'll use an off delay timer, so that you don't have to be standing right at the on the conveyor belts all the time. You can be in the office, Then once a certain amount of time has been counted, then the conveyor belts automatically switch off. Once the conveyor belts have switched off, of course, there will be an alarm system, or there will be a siren, or there will be some light, and then you will see that and then go to the conveyor belt or the production line, and then you can sample your product. So that's an off delay timer. A timer that is used when you want to achieve, you want the system to be switched off after a certain amount of time. The on delay timer, we've told you, is a timer that you want maybe a system to be on for a specified period of time. So it's the exact opposite of the off delay timer. I hope that is very clear. Now, in the exam, I'll give you typical scenarios that exist in the world today. And as an engineer, we'll ask you to suggest, if you were to design that system, which type of timer would be best suitable for your use. You should be able to determine different scenarios and different timers that are suitable for each of those scenarios. Okay, now, again, let's go back to the other part, which is the last one, which is the retentive on-off timer. RTO, that's the abbreviation. Now, each of these timers that I've talked about, the last two, the on delay timer and the off delay timer, have one big disadvantage. You see, in the world we live in, since it's not perfect, every time the power goes off for whatever reason, or every time an off instruction has been provided downstream, then the timer, that when I say, I'm saying if this output is given a logic off or a logic 0, okay, or a logic low, whatever logic it is, but it's logic. If that input is given a logic off or low, or even if there is a power failure or the power goes off, then what that means is the amount that was stored here when it was counting. So let me say when it was counting down the timer. Remember, timers are not counters. Timers count time, but we'll also see how counters help us in the next topic when we're talking about counters. But this is counting time. Timers will count down time or count up time, but we also have counters that can be used for other purposes. Anyway, before I digress, I was saying that if, for example, for any reason, an instruction off or low or a logic low has been provided on the timer input, or power has gone off, then the amount that was here when we were counting is going to, sorry, that amount is going to be lost. So, and that also happens with the on delay timer, that for cases where there is a power loss, or we have an off instruction or a 0 logic provided at the input of the timer for whatever reason, then the accumulated amount will be lost. Meaning, when we switch on or we switch back on the timer, then it will start afresh. So if the preset value was 10 seconds, then power went off when we were at 5. Then it means that when power goes off, we'll start again from 0. So let's say it found us at 5. It will find us back, we will have to go back to 0. And you see, time lost is never recovered. So because of that disadvantage, that these timers lose their memory while power, during a power loss or when provided with a logic 0, we needed a special timer that will retain its, or will hold on to its accumulated value even when the power is off, or when we have a power loss, or when you provide a logic 0 to its input. And therefore, that gave rise to the retentive on-off timer. So this is a very special timer, such that its accumulated value does not disappear after a power loss. Meaning, when the power is switched back on, then it continues from where it left its count. So this is the retentive timer. That's why it's called a retentive timer. It retains. So you have the timer still, you have the time base, you have the preset value, you have the accumulated value. Okay, and of course you have the enable bit, which is the timer output. I'm taking my time to label this because we agreed as one of the rules of ladder diagrams and instructions, labeling critical. And then of course, this is the timer input. So this timer, some books will call it a hold or store timer, because it holds on to the accumulated value. It stores the accumulated value. So that even when there are cases of an input that is 0 or logic low, the accumulated value is not lost. When that input is reversed back to high, or when power comes back, then the accumulated value continues from where it was previously before the power loss. So that is its main function, to be able to hold on or to store the accumulated time so that we don't lose that for whatever reason. So where do we use this timer? Of course, from the definition, you can see that we can say that this is best used where there can be a change in the rung state. When I say a change in the rung state means because this is connected to a rung, okay? So let's say this was a logic 1. So it gives a logic high to the timer. So the timer works. So if this state changes to 0, then now it's equivalent to the timer not working, because the timer is deactivated. When the timer is deactivated, we don't lose this value because we store it or we hold on to it. Okay, so that when this changes back to logic 1, then we can continue our count as usual. So we use it in cases where there is a change in the rung state, meaning we can have a logic 0 or a logic 1 at the input of the of your timer. We can use it during power loss, or there's a system interruption. Those are things that can happen, and they have happened before. So the beauty of this timer is that it retains or it holds its accumulated time despite changes in the rung state, despite power loss, despite any other form of interruption in the system. That is why we use the retentive on delay. Very, very important. Okay, because there are cases where we can't afford to resume counting from 0 again. Okay, so we have provided 3 main timers for the PLC operations in order to control PLC operations. I've told you again, for just like with the other PLC devices, the address is important. The preset value is important, especially if you're clicking and dragging these timers and setting them in the software. You have to ensure that you address it. Now, we agree that addressing is important because that is what specifies the memory location where the logic is stored. So if you don't have an address system, then we don't know what is stored in that area. The preset value will tell us what you are counting to, what's your target count. So that's very, very important from having as well. The timer base, I've told you, is also very important because this is the interval of count. Remember, ladies and gentlemen, I'll challenge you on this because this is why you are engineers. You're supposed to think outside the box. I might give you a timer, whichever timer it is, I won't specify. But let's say I provide a preset value, okay? And I also provide a time base value, okay? So the preset value is 10 seconds. Okay. Now you have two timers. You have two timers here. The preset value here is also 10 seconds. The time base here, let's say the time base here is 1 second. The time base here is 0.1 seconds. So now, which timer will take longer to count? Which timer will take longer to count? Remember, I told you, if you are to count 10 seconds as your preset value, and you're counting it at intervals of 10 seconds, then the accumulator here knows that the timer, or what I was calling you the timer timing bit, the TT, timer timing bit, will have to count 10 times, because we said when you have as a time base, if you multiply by the okay, let me not confuse you with that. Let me just explain this first before we do those multiplications, because some of you will just cram it. When we have 10 seconds as our target count of time, we want to count 10 seconds, and we want to count them at intervals of 1 second each. Then we are simply going to have 10 counts. So the accumulator value will be 1, then 2, then 3 at any given time, then 4 all the way up to 10. When the accumulator value reaches 10, then the done bit goes to logic 1, meaning we have achieved the count. So we need a logic 1 there. For this one, you can see it's counting in intervals of 0.1. 0.1. So the accumulator value here will be what value? Remember, it is counting in intervals of 1. So for it to achieve 10 seconds, you will have to count 100 times. So here, you only need 10 counts of time, but here you need 100 counts of time. So please take note of this. Whereas these two timers are exactly the same, the fact that I have changed what the time base is, this is just to emphasize the importance of the time base. The fact that I've changed what the time base is, this guy has to do 10 counts, while this guy has to do 100 counts for them to achieve the same amount of preset value, because the preset value here is 10 seconds and the preset value here is 100. Is also 10 seconds, not 100, sorry. The preset value here is also 10 seconds. However, this guy has to do 10 counts. Tick, 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 up to 10. This guy will have to do tick, 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 up to 10. Up to 10 seconds, but they will have been longer. So it has to count 100, while this guy has to only count 10. So the time base is a very, very important part, or a very, very important function of value in the timer to decide on. And when you're given a scenario of, maybe because you're designing, so you've been given a design specification, you have to pay very close attention to what the design question is asking, because then that will determine what value you set as the time base. Typically, you'll be told the preset value because that guy wants a certain interval. Or when a count has been reached, they know that I want this thing to do after every 20 seconds or after every 30 seconds. But then the time-based decision is on you for you to be able. But typically, if you're not given that, we assume that the time base is 1 second, meaning you're counting at intervals of 1 second, unless specified or unless it's explicitly mentioned in the question. Okay, but take note of that so that you're not confused. So the time base is quite important. For you who've operated the oscilloscope, you've seen the frequencies, the time base, how we usually have. So you have a signal like that, and vis-a-vis a signal like this for the same period of time. Okay, so you can see how many cycles here and how many cycles we have here. That's really the essence of the time base. Okay, the shortness of the count. Okay, good. Now, I have mentioned the key things that are, oh, there's one more, of course, here. The key things that you always have to look out for. Accumulated value. Okay. Then, of course, there are the other bits. Told you the enable bit, the timer timing bit. So these are called bits. Timer timing bit. Some people will just call it TT. And then, of course, I said the done bit. Okay. Some people, like, for example, I think in Allen Bradley and even in Siemens, the output bit is called the timer's done bit. Okay. Because it indicates the timer has reached its preset time. Okay. So it can be called the timer done bit. Again, there are different addressing based on the manufacturer. Some people will have addressing systems, maybe start from T0, T1, T2, you know, depending on the memory of the device. You can even have up to 255. So that therefore means you have 256 timers in your ladder diagram. It can accommodate up to 256 timers in your ladder diagram. Your ladder diagram has to be really, 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 really huge for you to have 256 timers in it. Okay. So examples that we give, because we just need you to illustrate, we'll only need up to maybe 4 or 5 timers. That's it. Because even if you remember your 4th year project, I think for the final, the 4th year project on the design of traffic lights in a 4-way junction, because there are 4 junctions, you need about 4 timers. Okay, so we don't use so many, but you can have up to 200, or projects where there are up to 250 plus timers in them, and they all can be accommodated. So some people will call them T0, T1, T3. Some manufacturers will call them T10, T20. Sorry. There are so many, I can't remember all of them. I'm just remembering off the cuff. So T10, T11, T12, then they go to T20, you know, T21, T23, or T22, you know. So what my point is, different manufacturers have their own way of ranging or counting or labeling or addressing, that's the word, addressing the timers. But we now know that as long as you have a data sheet, you will know what kind of addressing system that PLC manufacturer uses. So you don't need to cram any of this, okay? I would never test you on how to address a Rockwell PLC. No. I'll never ask you, how does ABB address its PLC? Because that is not for you to cram. That information is available in the data sheet. So you only simply look at it and then you use it. Okay. So even in your use of, or if I give you a design scenario in the exam, for example, I would not mind as long as you have an addressing system. I don't mind. You can choose an arbitrary one. You can come up with your own as long as it's consistent and it makes sense. Okay. So we are not restricting you here, especially because that information as engineers would be available in the data sheet. So you can always refer to it. So it's not something that I can test you on. There's no significance there. Okay. So I hope that is now very clear that we have 3 main types of timers and we use them for different scenarios or different control operations. So you just have to figure out exactly when you need to use it and which is the most important or the most relevant timer to use at any particular time. All right. Now let's do an example. I cannot do an example for all of them. The book by Petruzella has got several examples that makes use of the on delay timer, the off delay timer, and the retentive timer. So you can look at those at your own time. Remember, I'm only here to guide you through them. Okay. So I want us to continue with our example, if you remember from the previous class, we were having our ladder diagram here that we were coming up with. And the example we did, if I just remind you briefly, we were to create a PLC ladder diagram for motor control utilizing the holding logic. So here it was specific that we incorporate a start push button. Remember, again, I'll remind you just in case you forgot, because here it explicitly states that we incorporate a start push button. We know that a start push button is in the normally open position. So in the ladder diagram, we simply again add another normally open contact. We incorporate a stop push button. We know that a stop push button, a field device, is already in the normally closed position. So in the ladder diagram, we just put a normally open contact so that it works. Otherwise, if we put both of them as normally closed, then they are going to negate each other and it will not work. Then, of course, a motor thermal overload is a built-in system which is already in the normally open, in the normally closed position, because it's a normally closed contact. So in the ladder diagram, we simply use a normally open contact. And again, I will emphasize, because here we were explicitly asked to include these buttons, we had to have the setup where for the start push button, we know we are going to use that, so that in the PLC, we also use that, okay? This was for the start. For the stop push button, it's already normally closed as a field device. So in the PLC, we use a normally open. For the overload, again, it's already in the normally closed position. So in the PLC, we use a normally open contact, okay? However, if we weren't asked or we were not asked explicitly to use this, then this would stay as normally open, this would be normally closed, this would be normally closed, okay? If we were to simulate this without having to incorporate these field devices, then we know that the push button, the stop push button will be represented as a normally closed, and the overload is also represented as a normally closed. That was just a by the way to remind you for those who are still confused. Anyway, so remember, our idea here is to see how we now can incorporate a timer in this kind of setup. So let me just rephrase the question again for us to include the timer in it, okay? So the question here now is modify the previous example of motor control. It was motor control using it's a latching logic. So we want to modify that example that we use, by introducing a warning siren. In order to let operators know that the motor is about to start. Okay? So typically you'll get a question like that. You had constructed the ladder diagram, but now you have to improve upon it, because now we have to incorporate a system where the operators should know that the motor is about to start. In the other case, you just pressed a button, the start push button, and the motor ran. Okay, even when you release your press, if you release the press for the start push button, the motor continues to run because of the latching property. But now we want you to press the button, but instead of the motor running, we first hear a siren. And that siren will sound a warning for a period of time. And when we hear that warning as operators, we know that the motor is about to start. So that maybe if you are close by, we need to move away because of the dangers or for safety reasons. Okay. So from here, this is where you now figure out which is the best suitable timer to use for this. Because the reason why, yes, there's a warning siren, but that warning siren should be a gap between, because you have, we always know from our discussion there, you had the start push button. So if you did the motor start, then in the first case, the motor activated immediately. But now we want that if you press the motor start, it first goes to the siren. And then the motor is activated. So there's an intervention in between. And this siren, maybe it's for 10 seconds. Okay. So the siren will be on for 10 seconds and then the motor activates. So here we need a timer so that when the motor start button is pressed, it activates a timer instead of activating a motor. So you see here, the motor start was activating the motor. This is the button, okay? This was activating the motor directly. But now we want a case where we activate a siren. So basically a timer. And then as soon as that timer count has elapsed, it activates the motor. So this is where we need something like an on delay timer. Because remember, we can't use the off delay timer. The off delay timer will switch off the motor after a certain count of time has been reached. Here, we want the timer to count a certain value before the motor is switched on. So this is to switch on the motor after a period of time, not to switch it off. So that's why we need an on delay timer to switch the motor on after a certain period of time. Good. So now we need to incorporate an on timer. But remember, the output devices will also change because the output devices will include a siren, a field device. There will need to be a siren. Okay. Now, remember, you are from the first case and the second case, you can see that the second case has introduced two new actions. And that's why I don't want it to be lost to you. That's why I'm still interrogating the question. Two new actions will have to happen. There's got to be a siren. Okay? So because we need a siren, we'll also need to add a timer. So when the motor start push button is pressed, the siren goes off. So meaning it starts blaring its sound. And then we time that siren so that 10 seconds later, the siren switches off now and the motor is activated. So let's go again and list all inputs and outputs, because I told you that was the first step in any design, so that you know all the inputs you're working with and all the outputs you're working with. Now, it should not be a strange thing because we already did this in the previous example. We are simply going to improve on it. Okay? Okay. So we have the inputs. Let's list our inputs. Again, I think we were calling them M1 start. Okay, and we gave it an address. So apart from the address, what else did we give them? The wiring. So M1 start was an input. Okay, I think it was 1.0, 1 point something, 1 point something. So this is normally open contact, of course, because the start button. Told you all start buttons are usually in the normally open contact. So this is the start push button to switch on the motor. Okay, but in this case, it will have to go through a different device. It doesn't switch on the motor immediately. Of course, there's the stop, which doesn't change. The PLC wiring is normally closed. When I say PLC wiring, is, remember, in your PLC diagram, they are the devices that you click and drag. But then there are devices that you physically wire. You physically take a wire and connect. That is the PLC wiring. And it happens here where you have the field devices, that this is input field devices. And it also happens here when you have output field devices. So here you do a PLC wiring because you have to take physical wires and connect. And here also you have to do some PLC wiring because you have to take physical devices and connect. But whatever happens between the ladder diagram here is a click and drag. This is where the software is. So there's no physical wiring involved. You simply click and drag the icons and put them in place. Okay. But here you'll have to do the physical. That's why I indicate here what kind of wiring that is done in those devices. Again, the more examples you look at, the more this becomes easy peasy. So, of course, the other inputs, this is just borrowing from the previous case. But notice I'm rewriting everything so that I don't confuse it with the previous example. So you have 1.2, and this, of course, is also normally closed because this is a field device and it's closed. It's in the normally closed position. But now we have the extra output that we need. Okay, so this was the original setup even from the previous case. But now, so you can notice that the inputs that we have here is the same set of inputs we had in the previous case. Nothing has changed. Okay, so let's look at outputs. Here, we are going to have an extra output because remember, let's look at the outputs. In the previous case, we had the motor run. I think it was M1 run. And because it's an output, it is output 1.0. And of course, it was in the normally open because it's like this, just the output like that. Because if it were normally closed, then it would be something like that. So this was like from the previous example, we just had the normally open PLC wiring for the output. Okay. Now, what we are adding here is now the extra thing that I was telling you about, because now I told you the output must include a siren, because that siren is a device that has to be wired into your system so that it actually sounds and it warns the operators. So we can call it M1 siren, because now we are having it as it's a siren for our motor. So we can now give it a different addressing. So now it is output 1.1. Okay. Again, it's just in the normally open position, so that when it receives a logic 1, it sounds. When it receives a logic 0, it stops sounding. Okay. On off, on off. Okay. But now something needs to happen here. If you look at this scenario, we need to add an extra internal variable. And that is, we need to add, before we even add a timer, we need to add a start command. Because, ladies and gentlemen, I think, I've wrapped it off. In the previous case, we had start, and then it's connected to the motor. But now we have the start button that's connected to your siren. Okay, that's connected to the motor. Because when you start the button, the siren goes off, and within the siren, we need a timer. We need a timer so that when the the preset value of the timer is reached, then now we have the motor. So we need a start command for the motor. Because the start, remember, ladies and gentlemen, the start that we had, the start push button that we had is now sounding the siren. So we need a command. That's why we are calling it an internal variable. It's a command to start the motor. Because if you take the motor and connect it directly to the siren, it cannot work. That's why I told you, you have to think critically, logically, just look at it. If you take a motor and connect it to a siren, will it work? Of course it will not work. The only way it will work is if between the siren and the motor, there's a start, so that we know, I press this start push button, the motor sounds. I mean, the siren goes off, it starts sounding. Then I count 1, 2. So the siren is sounding, and I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The moment I reach 10, I need a start command for the motor, because as soon as the preset value of 10 is reached, then it needs to activate a start for the motor. The motor doesn't listen to sound, so that when the siren stops sounding, it starts automatically. No, the motor listens to a command. That command is what we are calling the internal variable start command. So that when the motor, because the siren is sounding, as soon as the siren stops sounding, then the start command is activated so that the motor can start running. Remember, the motor is not activated by a siren. The motor is activated by a start command. The motor cannot hear audio. The motor only needs a logic 1 or a logic 0. So for our case in our design, we just ensure as soon as the siren stops after 10 seconds, the start button is activated. The start command for the motor is activated. I hope that is clear, ladies and gentlemen. If it's not, I can repeat it for you. You just need to ask. So remember, we have some extra. I'm calling it extra because it's not a physical device. Extra start command. Remember, ladies and gentlemen, it is not a push button. When the siren goes off, I don't have to go and press the start push button. It's a start command. You see here, somebody has to physically press the button. Here, somebody has to physically press the stop button. Even here, there is a thermal overload that must happen before the downstream equipment is activated. Here, we need to add just a command, okay? So that it's the one that's responsible. So we can call it, and remember, because it's a command, it's not a physical device, we commit it to the memory of the PLC, okay? So let me just write it properly. Start command. This is now the one that's responsible for starting the motor, because the push button is now starting the siren. So we commit it to memory. So it's not an output, it's not an input. It's just memory, so that we just know that whenever we have achieved the timer, so when the timer done bit goes to 1, meaning the output of the timer, remember the done bit, we are done counting. When that done bit goes to 1, then the start command is given that logic 1. And then, of course, the motor picks up from there, and then the motor starts. So that's why we are committing this to memory. It's a command. It's not a button. We commit it to the memory of the PLC. That is not to say that the input addresses here and the output addresses here are not part of memory. They are also memory. But this is now a special memory where you have a command that you are committing this, I mean, you're committing that command to that memory. Now, because we are not categorizing it as either an input or an output. Then, of course, the elephant in the room. We've not added the elephant in the room. So we need to add the on delay timer. The on delay timer. So again, let me just address it as T1. Okay, you can have T1, T2, 3T, I mean, 4, T4, and so on. So this is to start the motor. This is the one that now, it's the delay timer for the motor. It's actually the motor delay timer. Now, again, remember, we are not wiring the timer. Okay, we're not wiring anything to the timer. It's part of the software that we include. Okay, remember the things that we were wiring, remember, are field devices. This is the field connection, even this. Because you have a physical siren, where you can hold it, you can touch it, and so you need to wire it into the PLC. Okay, you have a physical motor that needs to run, that needs to be wired into the PLC. You have a physical start push button. You have to wire it to the PLC, and so on and so forth. Good. So now we have included the things that we needed. Now you can see from the previous case, we've added the siren as a field device because it's a physical device, but we've added a start command for the timer. So the timer has been added and it's a start command as well. So please, ladies and gentlemen, remember this M1 stop, and the M1 toll, the thermal overload. Because in wiring, we use normally closed contacts. Okay? In the ladder diagram, we use normally open contacts. So when you're doing the physical wiring of these devices, you have to ensure that you wire them as normally closed contacts. So they are wired as normally closed contacts to the PLC inputs. But in the ladder diagram, in the software, we represent them with as normally open contacts. So let's see if we can come out with the ladder diagram and then explain it and see if it can work. Then tomorrow we'll improve on this again by now adding another set of instructions. So today I want to see how we can achieve this. Then I introduce what, because tomorrow is just 1 hour. We see if we can introduce another set of instructions into our design so that we can make it even more improved. Okay. That is, tomorrow we'll see if we can add a flasher circuit. But anyway, let's try and see if we can achieve this first of all. So let's draw this ladder diagram. Typically, there's one mark for drawing the rails. It's very easy. Now, because we drew this in the previous, I think, let me just show you. I don't want to reinvent the wheel for those who are in class. And I think now, I don't know, I think I already gave you these notes. You already see the circuit that was drawn for starting the motor. So that nothing changes with this. This remains exactly the same. That is the latching element of the circuit. So again, I'll just include that because here we've just incorporated another device. So it should not be lost to us. We're just incorporating another device. So basically we had this, then you had the stop, then you had the toll, then you had the output. But because this is a latching circuit, we branch out the output there. So I'll not write the addresses, ladies and gentlemen, because of time. So let me just say this was the start push button. We know this was the stop. This was the TOL. And this was the motor start. So this is start. Okay. And we had to, let me just call it output. Please remember, don't forget, I'm not just copying. Remember, the motor start, that is the M1.0, but then we also have the motor run. Notice we have the motor run and we have the motor start command. Okay. So let me call this the start command. We've listed them there. So this is also a start command. What we are calling I think M 1.0 something. So this is M 1.0. I think it's M 1.0, something like that. So this was the latching part of the circuit, where you have the start push button, and you also have the stop push button and the thermal overload. There's nothing beyond that. Now, the incorporation is what we want to do next. One, we want to see if we introduce a warning siren. How do we introduce a warning siren? Remember the sequence of operation. I press the start push button, which is the start command. Initially, I expected the motor to run. Remember, you were pressing the start push button and we were expecting the motor to run. But now that is not the case. I press the start push button. I expect the siren to start sounding. So therefore, this command here, this logic 1, remember, if we had a logic 1 here, then the motor would take it as a logic 1 and then starts running. But now we want this logic 1 not to start the motor, but to start the siren first. The motor is still not going on. Remember, it is to warn operators that the motor is about to start running. So therefore, we can take the output. We take this start command as an input. So therefore, you come and say, because the value, the logic value of this start command, of this output, becomes an input to the next sequence of operations. So now we say, let's take that. So this is now a start command. This is your start command. It's when you press that button. And so this is M1. It is still M1.0. Okay? So that if this is a logic 1, I know this is a logic 1. That's what I'm trying to say. If this is a logic 0, then this is also a logic 0. That's what I'm trying to say. So we are taking that output of the first case to be the input of the second case. So here you can see that this first rung is for latching. Okay? But this second rung, I want to activate the siren. That's what I want to do. I want to activate the siren. So meaning I'll take the start command. When I press that push button, I expect the siren to go on. So therefore, I expect the output to be a siren. This output here should be M1 siren. I think it was, I don't know its address, I don't remember, output something. So I expect this siren to go on, to start working. So that's what I expect. And I'm trying to follow with you logically so that we understand each step as we go along. In fact, typically, I would just connect this to this. It's not correct yet. You will see why it's not correct, but let me put it there first so that when I put it, you can understand first of all. So that here we can see that if the start push button is pressed, we can see that the start command output here would be 1. This would be logic 1. Let me use a different marker. We'll be having a logic 1 here. And therefore, we expect this to be a logic 1 and this to be a logic 1. And therefore, the siren, which is a field device, something that's blaring sound out here, is connected to it. Okay? But remember, when the siren goes off, we want a timer. So this is not a complete diagram. I'm simply trying to see sequentially. We'll come back and readjust the diagram accordingly. Let's just go step by step because I don't want anyone confused. I'll come back and readjust the diagram. There's something that's still off there. But now I also want to know that as the siren is sounding, the timer also needs to start timing. So I can still use the same start command. Now, I still want to borrow this same start command. So I simply have to draw it down here again. Because this is now for the timer. Okay. This same start command with its address, I think it's M1.0. Okay. I'm using that start command, meaning I'm using that logic state to control a timer. So I'll connect a timer there. and we say timer on delay, and you have to write it as timer on delay, like that. Now, because it's very difficult to, and maybe we label it as T1, that was the address, but because it's very difficult to include all the functions here, I'll include this because otherwise it will be a very big diagram. I'll just need to know this is the start. Okay, we know that in here is where it starts, or the timer is. Okay, then I need to have a preset value. Okay, I don't need to indicate the accumulator here. I just need to know there should be a done. There's a done bit here. So let me just say done. So the done is here. The preset value is given, let's say we are taking 10 seconds, 10 seconds. And then now, once those 10 seconds have elapsed, then now we have the motor one, not start, motor one run. Remember, there's motor one start, which is a start push button, but now there's a motor one run, which is now activating the physical motor is outside here. This is a physical siren outside here that's blaring. And so please take note. Our circuit is not complete, but I will show you why. Let's just think critically, logically. So we have the latching circuit. And remember, the latching is only such that when somebody presses the start push button, even if they stop that pressing, the motor continues working. So that's the essence of the first part of the circuit. The first rung, it's just to latch, to hold on to the state until an instruction has been provided so that it changes its state. So remember the output of the first rung is a start command. And so we are using that start command in two ways. Number one, we have brought it as an input to help the siren go off. Because I expect that if I press that green button, two things will happen. Number one, the siren will start blaring, which is the second rung. The third rung is the timer starts counting. And then after 10 seconds, the done bit would be a logic 1. And that logic would be transferred to the output. That logic is actually to connect it properly so that you don't get confused. You see where this done bit is? Because the done bit, as soon as the counting has been done, the done bit is the one that's connected to this coil here, like this. So M1 run is connected to the done bit because the done bit goes to a logic high as soon as the 10 seconds has elapsed, meaning as soon as the accumulated value is equal to the preset value, then the done bit goes to a logic 1. So as soon as the done bit gets to a logic 1, the motor is then now receiving that as an instruction to start running. But at least we'll have achieved a delay of 10 seconds before it starts running. Now, there's something missing, something very critical that is missing from this circuit. And I'll tell you what it is. You see, we have the motor run instruction. Now, again, I welcome us to think logically. We have a siren that is blaring for 10 seconds. As soon as the siren stops blaring, after 10 seconds, we have a motor that automatically now starts running. Now, the question is, does the motor, after 10 seconds, does it, if the motor follows the timer, because the motor waits for the done bit to be logic 1 before it starts running. But we were using, so remember, when we have a start command, the siren is blaring, but at the same time, the timer is counting. So I am wondering, this M1 run, is the motor running, how does it affect the siren? Meaning, as soon as the motor starts running, is there a possibility that our motor would be running and the siren is still running? I'll say it again, maybe it wasn't clear. You see, Here in our circuit, we have connected the timer to be the one controlling the motor. So that in our circuit here, as it is, in our ladder diagram as it is, as soon as we have reached the 10 seconds count, the motor starts running. And yet, we also had a similar instruction for the siren, that the siren, as soon as you press the push button, the siren goes blaring, starts blaring. But now, what will stop the siren from blaring? Because the siren has not been connected to the timer. You can see that the siren belongs to rung 2 and the timer belongs to rung 3. We have to connect this in such a way that as soon as the motor starts running, we expect that the siren would go off, should stop, because the way we have set up this circuit is such that if you think about it critically, when we press our start button, the siren starts blaring. And then the timer starts counting. 10 seconds later, the motor starts running. But that did not stop the siren. So we must have a mechanism for stopping the siren. Why? When the motor is running. So that the siren and the motor cannot be running at the same time. Because that beats the logic. The siren was to warn us that the motor is to start running. So when the siren is running and the motor is running, then what is the siren doing? What is its function? So therefore, we need a system, or that we have to improve this circuit such that when the motor is running, it ensures that the siren is off. So the only way engineers do that is to ensure that you use the running of the motor to stop the siren, because we don't expect the siren to be blaring at the same time the motor is running. And because we have not connected the siren and the timer on the same rung, you can see that they're on different rungs. So while the siren would be blaring away, the timer would be counting 10 seconds. As soon as the timer has counted the 10 seconds, the motor starts running. But now what stops the siren so that we don't have the two of them running simultaneously? So the best way to do that is to improve on rung number 3. So you come and change things here. And so think about it. We can connect the logic such that every time the motor runs, because we know the motor will be running when this output is at logic 1, that we should agree that every time the motor, the only condition for this motor to run is for this to be at logic 1. So we can connect this in such a way that when this is logic 1, this is logic 0. So that the two of them cannot be running at the same time. We don't expect the siren to be blaring and the motor running at the same time. The siren's work was to warn us. 10 seconds later, it's supposed to stop, then the motor picks up. But because we've not connected them on the same rung, we have to connect or change this rung number 2 such that the state of the state of the motor running is always the opposite of the state of the siren, such that if the siren is at logic 1, we know that the motor is logic 0. And when the motor is logic 1, the siren is at logic 0. So that the two of them have opposite logic states at any given time. That is the only way to ensure that they are not running at the same time. Otherwise, now you will see that the case, if we leave it like this, we'll be having logic 1 here. So the siren is blaring away. The timer will also be counting 10 seconds. Then it changes these states to logic 1. So we have both of them at logic 1 at the same time, which is wrong. We expect one of them to be a logic 0 when the other is a logic 1. So the best way to do that is to introduce an anomaly. How do you negate one of these? The only way we can negate a logic is to use the normally closed contact. So the best way is to do this. We can decide that here we connect a normally closed contact. But this normally closed contact, please take note, is M1 run. It is this guy here that we are calling output 1.0, I think. Okay? Output 1.0. So now think about it. Let's now logically look at this stuff. The first rung, we don't have a problem with. We studied in the previous class. But now let's take a note. This guy, let's say you've pressed the green button. So this guy will definitely go to logic 1. Let's just think critically. I've pressed the green button, which is the start button. The start command here will go to a logic 1. When the start command goes to a logic 1, then of course, because it's the same memory location, this is logic 1 and this is logic 1, because they're all in the same memory location. It's the same device anyway. So we have logic 1 here, logic 1 here, logic 1 here. What is, now we are providing a logic 1, clearly. M1 run at this time, there's not, the logic here is 0. It's not running because the logic there is 0. The only way the motor will start running is if this logic is 1, but this logic is 0, because at first we don't expect the motor to run. We want the siren to be blaring. So the logic for this is 0 at this point because the motor is not running at this point. So the logic for this is 0. Remember, a normally closed contact is such that if you give it a logic 0, it passes logic. But if you give it a logic 1, it blocks logic from passing through. So in this case, it is a logic 0 because it's the same logic as the motor, the output of the motor. So you can see that it is a logic 0, and that means it passes logic. So the start command is at logic 1. M1 run is at logic 0, meaning it passes logic. Its output is a 1. For those who will be confused, it means, let me make it very clear. It means if the start is pressed, we have a logic 1, meaning we have provided a logic 1 here. This is a normally open contact. If you give it a logic 1, it gives out a logic 1. But the output, the motor is not running. So the logic for the motor here is 0. And because this is a normally closed contact, it's a NOT gate. You give it a logic 0, it gives you a logic 1, meaning it's allowing logic to pass through. So its output is 1. So the output here is 1, and this output here is 1. So we expect 1 and 1 to give us 1. I'll repeat that because I know somebody somewhere is confused. Take my time again. Remember, we have a logic 1 here. Because this is M10, I think we call it M10. Everything in our ladder diagram that is M10 will take that same logic. So this guy will go to logic 1. This guy will go to logic 1. Everything because it's the same memory location. Remember, this is 0 because it's not running. Initially, the motor is off. So meaning the logic state there is 0. The motor is off. The logic state there is 0. But because we pressed the button, the push button, then we are having the start command, rung number 1. At the end, we have logic 1. Rung number 2 at the beginning, because it's the same memory location, it's logic 1. Rung number 3, again logic 1, because it's the same memory location. They are all M1. Even this one is M1.0, okay? But now let's look at this. A normally open contact, if given logic 0, the output is a logic 0. But if it's given a logic 1, then the output is a logic 1. Now, because the motor here is not running, it means this is also having a logic 0, because the motor is not running yet. But because this is put here as a normally closed contact, we expect that its output would be a logic 1, meaning you give a normally closed contact a logic 0, it passes logic, meaning it allows logic to pass through, so its output is 1. So you can clearly see here that by pressing the button, I already have logic 1 here. This is logic 1, and I have logic 1 here because its input is 0. So the output we know is 1 because it's a NOT gate. So 1 and 1 from our analysis before, they are two connected in series. If they are connected in parallel, they would be 1 or 1, but there they're connected in series. So 1 and 1 would give us a logic 1, and therefore the siren goes off. Now, because the siren is now blaring, remember, we had a logic 1 rung number 3 now. We have a logic 1 here. When you have a logic 1, what happens is we get a logic 1 at the output because that's a normally open contact. So we have the output there as logic 1. When we have the output as logic 1, the timer is activated to start timing. So it means we now start counting 10 seconds. 10 seconds later, you get a logic 1 at the output of the timer because it simply delays the input. It gets an input, it delays that input for a period of time, then it allows it at the output. So because it got a logic 1, it delayed it for 10 seconds, and then now we get that logic at the output after 10 seconds. That's the essence of the timer. We are delaying the logic at its input for a period of time before we present that logic to the output. It's like saving. Somebody gives you 10 shillings and tells you, give me after 1 month. So after 1 month, you still get 10 shillings, but a time has elapsed. So once you get a logic 1 here, then of course this guy changes to a logic 1. And when it changes to a logic 1, the motor starts running. But remember, we say the motor, when it's running, we don't expect the siren to be blaring. So as soon as the motor starts running, meaning as soon as we get a logic 1 here at the output, what happens? This is adjusted because it's the same memory location. This is adjusted to logic 1. And if it's adjusted to logic 1, output now becomes logic 0. We know that 1 and 0 is 0. So this becomes logic 0. I'll repeat that for the last time. Just the sequence at this point. The timer counts, gets its logic out as 1. The done bit becomes a logic 1. Because the motor output here becomes a logic 1, because the done bit is a logic 1, the motor output becomes a logic 1. As soon as the motor output becomes a logic 1, we know that because this is the same thing here, is the same address, meaning we still have a logic 1 here, because it's the same address, and because this is a NOT gate, that converts this back to a logic 0, and therefore this siren becomes a logic 0. So therefore, as soon as the motor starts running, the siren stops blaring. The two of them cannot be logic 1 at the same time. So ladies and gentlemen, we know that whenever you draw a ladder diagram, you are expected to indicate, to provide comments on the operation of your circuit or of your ladder diagram. So in order to do that, we say it's very difficult to write those comments in the ladder diagram because you can already see that our ladder diagram is congested. So the best way is to write them at the bottom, okay? So you can indicate something here, comments. And I expect this for all your designs, that at the end, you have to write for me comments. And those comments are simply explanation on what happens to your circuit. Okay, so you can indicate, and it's rung by rung. So you can say for rung 1, we can just say, because we did this in the previous class, works the same, can just say works the same as the standard motor control latching logic. Somebody reads that and quickly understands, okay? So that we know that, okay, you had the latching logic in rung 1. So you can even indicate rung 2. You don't have to say rung 1, rung 2. You can probably just explain the whole thing in step by step. You don't have to specify rung 1, rung 2, rung 3. I'm just indicating this because we only have 3 rungs, so it's easy to quickly indicate what happens, okay? So we can say maybe after rung 1 is scanned, remember the scan cycle, we have the second rung. In fact, let me not say after the rung 1 is scanned. Let me just say what happens in the second rung. So if, just indicate here, if the start command is true, if start command is true, Okay, notice it's in capital letters, not the true of verb that we usually use in English. This is a state. So if the start command is true, and we know that it comes true from the motor control latching logic. Okay, if that command is true and M1 run output, M1 run output is false. Okay, and the reason why M1 output is false is because the motor is not running. Motor is not running at that stage. The motor is still not running. So the output for M1 run, this is for rank 2, is so the condition of the output is false, then we expect then the siren output is activated. Yeah. So that it's what I was saying. If we get a logic 1 for this guy here, and we get a logic 0 for this guy, and we know that because it's a normally closed contact, if it gets a logic 0, it passes logic. So then the motor will get logic 1, and therefore it starts running. It's activated. The siren is activated. So that is basically what rank 2 does. Okay. Then now we go to the last rank 3. And for rank 3, again, it's simply to explain how the timer works. So here you can say, because we already had, so after the start command, because the start command was already true, is true. After the start command is true for 10 seconds, okay, and that 10 seconds is a preset value. So let me just say preset time. Okay. Then T1, which is the timer, the on delay timer, T1 on delay timer will activate the M1 run output. So therefore motor starts running. Therefore M1, let me just say motor starts running. Okay, but we know the story does not end there, because the motor starts running, the siren is still activated. Okay, and remember the PLC is such that we had agreed before. The motor starts running, the siren is still activated. Remember, the reason is, remember the way the scan cycle works. It will run like this. It will come and check this, all this, then it comes to this guy here and then runs like that. And then you see the motor is running at this point. The motor is activated there. The siren is activated at that point. And then this guy comes here and then starts again and comes here at the output. Then as soon as it finishes, it goes back. It goes back to check and update all the other conditions. So therefore, here you must also indicate that we have to indicate, let me just indicate here that we have to indicate on the second rung, M1 run output is normally closed. Okay, is normally closed. So when when it's no, I want to include the output. So I just want to write one word one sentence to explain this. So when M1 run output is true, then logic flows and the siren output goes false and switches off. That's what I wanted to say. Okay. So basically, you're not explaining much. You're simply indicating so that somebody can read this quickly and understand. So what basically I've done is I've indicated what rang 1 is. It's a latching circuit. So that we can see. It's common. It's known. It's standard, that is. Number 2, we see that number 2 is for the siren to come on. And so you just need a start command to be true, and then, of course, the M1 run output, because it's a normally closed contact, to be false. Then the siren output would be activated. So the siren is off, blaring away. Then we are in rank 3. The start command was true anyway, but now its output is delayed by 10 seconds by that timer. The timer delays that output by 10 seconds. As soon as the 10 seconds elapse, that output is presented to the M1 run output. The motor starts running. But because the motor is running and the siren was blaring away, the state of the motor running is going to change the state of the siren, because the M1 run is connected in the second run as a normally closed contact, so that when you give it a logic 1, then it blocks logic. So meaning, as soon as M1 run output is activated as a logic true, then we know that the siren will have to go false. Okay, then it stops running. So basically, this is how you introduce a design such that you're able to have this system to work properly. So please note, this is a very typical question that I would definitely ask you, maybe in a different way, but this is how you come up with a design. You have to write the outputs, you have to write the inputs, of course, and you have to see all the commands, even the ones that are connected to memory, the extra commands. You include them, and of course, the instructions like the on delay timer. This is how you include them in your circuit, and that then work from there. Now, remember, we started from just starting and stopping a motor. Then we went into latching onto the state of the motor, such that even when you stop pressing the push button, the motor continues running. Okay? But now we went now to using a timer, so that we now have a siren that blares off for about 10 seconds before the motor starts running. But now we need to readjust again. We want to improve on this circuit. So that improvement is what I'll do in the last class tomorrow before I move. And then I'll be done with timers. I'll move to counters. Okay. So now tomorrow, and this is why I'm telling you, I want you to start thinking about it, because our time is almost up. Now, we have made use of an on delay timer. But I told you, I want us to make use. So I don't want to do off delay timer, because it's just working in the opposite way of the on delay timer. But I want to make use of the on off timer. Okay. We want to have a flasher circuit, meaning I want to ensure we want to have an output that has lights flash on and off. So you have two sequences of both on and off. So we'll have to develop a code tomorrow such that you have a state where we have the motor, but we now have a flashing warning light. So the flashing warning light, and remember flashing is on, off, so that it activates after the siren has finished and the motor starts running. So please now remember, we want a case where you switch on the button or you press your green button and the siren starts blaring. And we have a flashing or a warning light, because there are people who might not hear, but they can see. So those who can see can look at the flashing warning light, but those who can hear will listen to the siren, and then we have our motor running, okay? So we'll see how to introduce that. So two things that you need to study on your own that I'm not going to cover here is you can cascade timers. So look at reasons why you can cascade timers. You might go to the market and find a timer that is limited. So if you want an extended period of timing, then you can cascade two timers together to give you that extended period. So the first timer would count up to maybe 2,000 seconds, and maybe that is its limit. Then the other one needs to pick up from there and count another 1,000 so that you have a total of 3,000 seconds. I'm not going to do this because it's a very simple thing. You just need to check that book that I gave you. So you can cascade timers. But the case that I'm talking about here is we'll use timers. Here, you remember we used only a timer once. It was only in one rung. But tomorrow, we'll see how we can use timers in different rungs, but we want to achieve the flashing system, where you want the system to start flashing, and as it is flashing, the siren is also blaring, and then the motor starts running, so that you are able to warn people who are visually impaired and also who are audially impaired. Okay, good. So if there are any questions, please ask. But this is the end of our class today. We have about 14 minutes to the end, but I am preparing for the next class. So any questions, please do ask. This is the time where I expect that you really understand the workings of a ladder diagram. Because the moment I am done with the timers and the counters, I will not be referring specifically to ladder diagram. I'll be referring a lot to other instructions that don't need me to draw a ladder diagram. So this is the time. Yes, Ochor, go ahead.
Yes, thank you. I have 3 questions. The first one, let's say in the example we were looking at today, after 10 seconds of the timer on delay, now that's when the motor will run. So let's say just before the 10 seconds elapsed, let's say 9 seconds, the stop push button was was pushed. What would happen?
Okay, let me answer that because I don't have a place to note them down. So let's say the timer was timing, and then before it reaches the 10 seconds have elapsed, somebody has pressed the stop push button. So remember, Ochor, the first rung of our circuit. Okay, sorry, I had to stop sharing, but I think some people would visually need illustrations. So let's look at our rung. So our timer goes on here. We expect a logic 1 at the output after 10 seconds. But before those 10 seconds elapses, somebody presses the stop push button. So the stop push button is this guy here. So you activate this button. What would happen? Clearly, and that should make sense. When you press the stop push button, then of course you will have the start command. You'll have a logic 0 here. So the stop push button, remember, this was a latching circuit. The latching circuit was such that even if I stop pressing the start push button, the motor will still run until I press the stop push button. So this is like the override button. If I press that stop push button, because it can be an emergency button, everything goes off. So if the motor had not started running, it will not run, of course, and of course the siren will also go off. Why? Because the moment you press the stop push button, this guy becomes a logic 0. So then This is logic 0 here. This is logic 0. Definitely, the siren will go off, meaning it will be deactivated, and even the motor, because it was not running, it will now not run, and the timer will lose the count. So even when you press the start again, the timer will not know where it was. It will start afresh. Okay, I hope that makes it clear. Whenever you press the stop button, this is like an emergency button. Whenever it is pressed, all functions of your output will go off. So in this case, it found as the motor had not started running, but the siren was blaring. The siren will just go off, and the motor, of course, will not run, because the stop push button gives the start command a logic 0. And therefore, you'll have a logic 0 at the siren, which is rank 2. You'll have a logic 0 at the timer, which is rank 3. So everything again will just go to 0. That is what will happen. Is that okay?
Yes, thank you.
Okay,
The second was the arrangement of the ranks. Is it, in our example, is it fixed, or we could have maybe the siren rank 2 being rank 1, and the latching one maybe being in rank 2, and the timer in any other order? Is it fixed?
Now, that's a very good question, actually. And I have to let you guys know. The ordering of the ranks are very, very important. You cannot latch the circuit at the end of the rung. We start the circuit with a start push button. That's the sequence of stuff. The first command is to press a push button. That's what starts the entire circuit. And so we don't expect somebody to take this rung to number 3 and then take rung number 3 to number 1. One, think sequentially on how you want your stuff to operate. That will determine what comes in what rung. And number 2, once you have ordered your rungs properly, please remember that we are focused on the scan cycle. So assume you are the processor. You are the one to process all this information using that scan cycle. You read, you execute, and then you update. So do you want to start reading, like when I give you a book, do you want to read from page 10 coming back to page 1, or you want to read from page 1 going to page 10? The sequence is very important because the scan cycle needs to follow the proper sequence of first reading instructions and then executing them and then updating the commands. So there are cases where you have to reorder the rungs the reordering of the rung is purely based on the operation, the control operation that you want to achieve. So you cannot order rungs haphazardly. It must be sequential in the order in which the whole process is occurring, or the order in which you want to achieve the control. You cannot jumble them up and assume that the system will just work properly. In fact, that is why I expect the last device that is connected to the motor, the device that would be connected to the field device outside here, the output has to be at the last output has to be at the bottom of the rung. I mean, the last rung. The last output, this guy here, has to be the last person on the last rung. We cannot have this M1 run here. This guy, we cannot have this guy brought up here. No. Sequentially, and for ease of following, and also for the sake of the scan cycle, everything has to be sequential in the right order. I know there are some designs that are a little complex that would require that sometimes we borrow this output and we bring it into another rung in between here. That is still fine, but we have to remember that the last instruction is obtained from the last rung, the rightmost. The last instruction that then goes to the field device is obtained from the last rung, okay, and to the rightmost, because top, bottom, left to right. That's the sequence. So we don't expect the output field device to obtain its instruction from the leftmost devices. No. So please follow that sequence. Last question.
Yes, the last one. We gave the timer a kind of a black box representation, I'd say instruction, but I was kind of firing, what kind of internal circuitry and maybe components does it have so that they can achieve their functionality?
Okay. Now, I don't know. I want you to go and read about it on your own because it's very simple information. But if you open up the timer, like if you have the time, I'm just doing it quickly before our time elapses. We have about 6 minutes. So you have a timer like the on delay timer that we have just done today. Remember, we had, so this was the done bit. So the timer itself, if you open it up, it simply consists of normally open contacts, by the way. It's a very simple circuit. It's not, it's a circuit that's connected, is represented by this symbol, but it is still the same circuit that we have done before. So for example, if you open up an on delay timer, what you'll get is a circuit like this. A very simple circuit. You can go and read about it. So this is the let me just call this I1, the first input, okay? And then this is the timer. So this is actually the timer output. Please note that this thing had a timer output and a done bit, okay? And then you have you take this, let me call this T1, okay? And you bring it here as an input. Then you get your Q1. And remember that your Q1 is the output of the timer, which is there. There's a timer output, please, and there's also the done bit. So Q1 is this done bit here. So you'll be having something like, you have a normally open contact, which when activated, activates the timer output here. This timer output then activates the done bit. This is where the done bit is. Okay, so it's a simple circuit. It's just having a normally open contact that's connected in a ladder diagram format. That's what's inside the box here. This is what we have here. Okay, so basically, even if it varies, it's only a slight variation. But the typical structure of a timer, if you open it up and construct a ladder diagram for it, it's like this. Okay, it's a very simple. Of course, remember this output here is what I have brought here. Okay, yeah. So that is it. But you can read more about it, and if you don't understand, probably I can explain further. But that should pique your interest as a self-learner, that you want to figure out what is inside this box. Good question as well. Any other question, guys? Because of time, I need to cover at least another student should. Ogola, go ahead.
Yeah, excuse me, sir. I was asking, how is the scanning taking place sequentially when we have the same command in the second and the third run, and also what is the implication of having a off delay timer where we have the normally closed in the second run? Yeah.
Okay, if I hear you correctly, you're asking what is the sequential ordering that I told you here is for us designers to understand, but I told you the key thing is the scan cycle. The scan cycle is what determines how you design your ladder diagram, because you have to think, how will the processor run through and understand each? And remember, the scan cycle is such that the first thing it does is it reads the sort of logic states of each of these. And then once it reads, it then executes and then updates and then repeats the whole process. So the sequence is such that it will know the state of this guy, the state of this guy, the state of this guy, but it will not execute immediately. Remember, I told you that the scan cycle happens so fast in milliseconds. So what needs to happen is it runs through the entire set of your ladder diagram, the entire set, and reads the state of each of the contacts and the outputs. Then it executes instructions as indicated by each of the inputs. And then remember, it has even read the states of the outputs in the first instance. So the first instance is simply read. So it's a quick scan by trying to know what is the current state of each input and output in this device. Once that is done, it quickly now knows what were the instructions provided at the inputs, and so that it can execute those instructions quickly. And those instructions are like transfer logic 1 to the output, transfer logic 2, logic 0 to the output, and stuff like that. So it will even know the output logic, but it is not updating those until it finishes the first scan. So within the first scan, remember there's a read. Within just one scan, there's a read, there's an execute, and then once it has completed the first read and execute, at the end, it now updates the entire state of the outputs, and then it repeats itself. So for me, what I meant is the sequence is for me to follow through how I put in rang 1, rang 2, rang 3, I have to understand how the scan cycle operates. So therefore, it's very important, that sequence of operation and how I order my rangs. Number 2, you asked about having an off delay timer instead of the M1 rang. Now, I want to tell you, this is not the only design that you can have for this kind of setup. Somebody can come up with their own design. And yes, it is true that maybe I can incorporate an off delay timer, okay, instead of an on delay timer. So then if I incorporate an off delay timer, the way I connect my circuit is going to be a little bit different. So that the off delay timer, because we know what an off delay timer does, after a certain period has elapsed, it switches off. So in this case, it will switch off the siren after a certain period of time has elapsed. But remember, our discussion here was using an on delay timer. So it is true, we can decide otherwise that we want to use an off delay timer, so that instead of having this normally closed contact, we are going to use an off delay timer to ensure that after a period has elapsed, the siren will go off. The only thing now is the output of your off delay timer is going to affect the siren. It's going to switch off the siren. But then what are you going to connect to the M1 run? Are you going to use, what else now are you going to connect? Because the output, unless now you again say, I'm going to take the output of that timer to be an input so that I use it to now activate the motor. So as soon as the motor stops, as soon as the off delay timer reaches 0, it has counted down to 0, the siren goes off. Then I take that logic to rang number 3 to stop the motor. To start the motor, which is okay. So you can use an off delay timer. And maybe those are some of the questions I'll ask you in an exam. So I'll give you an on delay timer. I tell you to use an off delay timer instead in your circuit. Kuna mtu mwingine akona swali, because our time is up and I have another class which has already begun. I don't see any other hands. I didn't check
in the chat.
Yeah. Oh my. Because of time, let me quickly see if I can check the chat. Yeah. Okay, I see. According to the last statement we have written, the M1 rang output is true. Don't we expect the siren output to still be true? So maybe it's just the way you've understood the question. The statement. Maybe the statement doesn't quite make sense. But what I mean is, if you have the M1 rang output to be true, by virtue of saying that it is true, it means that since it is a normally closed contact, that I'm talking about the second rang, since it is a normally closed contact, if the output is true, it means it's passing logic. If the output is true, it's blocking logic. Yes, please, a normally closed contact is such that if it's given a logic 0, then it passes logic. That means if it's given a logic false, then logic is passing. If it's given a logic true, then logic is blocked. So when we say that M1 M1 run output is true, we are talking about the output of rank 3. Remember, the output is in rank 3. In rank 2, that's an input. It's not an output. So the M1 rank output is true. The output is true. But in the second rank, it is a normally closed contact. That's an input. So that input is false. So please note that the outputs and inputs are different. So the rank 3, we are talking about the M1 rank output. It's true. Now, what happens when you give a true logic to a normally closed contact? What happens? That's what you need to consider. I believe that M1 rank output is not a function. So when its input is true, the output will be false. Hence, the siren output will be false. Again, this is now jargon of trying to explain ourselves. What I meant, and in closing, because of time, ladies and gentlemen, please always remember, in PLC, when we talk about output, we are not talking about the output of, okay, let me just quickly share that again, because I was only using that to try and explain to you guys, but now it's confusing again. Remember, when you have this, guys, we are not considering this as input and this is output. It's going to confuse you because we have input. PLC only understands this. If I draw this, that is understood as an input. If I draw this, it's understood as an output. So when I use this in rank 2, and this is rank 3, if this is true, we know that the logic state there is 1. But because we are using it as an input, so let's say this is M1 0.1 and this is M1 0.1. Because this is logic true, we are thinking, we are now making this logic true. So what happens when you have a logic true or a logic 1 to a normally closed contact? A normally closed contact, when you have a logic true in its memory, it simply blocks. It blocks logic from passing through, meaning whatever gets to the output that's connected to it is 0. That's what we mean. And whenever we have a logic false here, it therefore means that the output is a logic false. But because we have an input here, which is of the same address, so that logic there is 0. But what happens when you provide a logic state of 0 to a normally closed contact? It allows logic to pass through, meaning the output that's connected to that device will be having a logic 1. That is what we are referring to. That's what we mean. So maybe the statement might be ambiguous, it might be confusing, but please note, we are not meaning that here I provide an input and I get an output there. No. We are simply saying we know the operation of a normally open contact and a normally closed contact. So we know that if I provide logic 1 to a normally open contact, it allows logic to pass through. But if I provide a logic 1 to a normally closed contact, it blocks logic from passing through, meaning it will give out the state that will be in the next output is 0. That's what we mean. So please note, so here we shouldn't refer to outputs because this is an input device. It's not an output. Output, so when I say that the output logic, this is the output. This is the output that I'm talking about. But we understand that that output logic, if used as an input in the normally closed position, what does it do? And if it's used as a logic high in the normally closed position, what does that effect do? Okay, so outputs, let's stick to this guy. Inputs, let's stick to this guy. Okay, so even this guy, let's not say that you give it an input and it gives you an output. It will totally confuse the whole scenario. Ladies and gentlemen, I have to go. Maybe because we are still doing this same question tomorrow, let's answer those questions again in the next class tomorrow, for those who probably would still be confused. But for now, let me end my class so that I can also serve the others. Thank you guys very much. Have a good day.